And we're recording. Okay, so we've done free fall so far, and if you caught the music when you came into class, it was Tom Petty singing Free Fall. That was Miss Humphrey's idea. I thought it was pretty good. On page 36 are the generic notes and understanding of what up and down motion is. So as a quick review, we've done free fall so far. That was last week, where we drop a ball, release a ball, let go of something. And we learned a few things about that, that V1 is 0, the instant I let go of something, it hasn't started to move yet. And the acceleration pulling it down is 9.8 meters per second squared, which is due to the Earth's gravitational pull. If we went to Mars, if we went to Neptune, if we went to the moon and let go of things, V1 would be 0, but A would be something different than 9.8. Where that 9.8 comes from, we'll learn more about when we get to Unit 4, which is on gravity. Now, this week, we're talking about things going up and down. Straight up and straight down. We are going to do up, down, and over. We'll talk about that when we get to Unit 4. But actually, many of the things that we're learning today about straight up and straight down is still true about up, over, and down. When I throw something up and down, it can be either symmetrical or asymmetrical. Symmetrical means really this. That's what defines symmetrical. The fact that the distance up is the same as the distance down, as this picture shows. If something is asymmetrical, then the distance up and down is not equal. These aren't super tough, but they're just a little bit more difficult, and they take a couple days to do, so that's what we're thinking about, maybe not worrying about them this unit. If the distance up is the same as the distance down, then other things are true. The time up is the same as the time down. And the velocity initially, when we launch it, is going to be equal to the final impact velocity. Because gravity has the same distance and time to slow it down as it has to speed it back up. So the great thing about symmetrical problems is the up and down are mirrored images of each other, which means in an up and down problem that's symmetrical, I only have to do either the up part or the down part because they're literally mirrored images of each other. For the asymmetrical, those things aren't true. None of those things are equal, and that's what makes it a little bit more challenging. And again, we're not going to worry about doing those problems, but we'll have a video on it on Buzz for those that are interested. So, if I do the up part, we're going to be decelerating at 9.8 meters per second squared. If I do the down part, we're going to be accelerating at 9.8 meters per second squared. Whether it's decelerating or accelerating, the acceleration is always going to be 9.8 meters per second squared. A helpful hint is drawing pictures. That's really important with the asymmetrical, but I'll even draw some generic little pictures with the symmetrical. These two questions were on page 34. So take a peek back to page 34, our PKP page, prior knowledge probes, that we looked at a couple days ago. And I'm going to give you about 30 seconds to revisit that and write some values down if you didn't write them down, or change your values if you now have a different perspective of what you think those are. Because I'm going to answer those questions in 30 seconds. So starting now, some time to think. All right, let's pop back to page 36, and let's write the correct answers here. Get your chat ready, because I'm going to have you chat to me the questions as I ask them. So, a ball, a rock, a whatever is thrown straight up. And as it goes straight up, we want to find the velocity at the very top of its path and the acceleration. So let's do the velocity first. A ball is thrown straight up. At the very top of its path, what we call the apex, what do you think the velocity value is? Chat me the answer. A couple more coming in. Got about 20 of you in so far. Let's get a few more in. All right, so the two answers we got coming in, 9.8 and 0. One of those is correct. The vast majority of you got this one correct. It is, in fact, 0 meters per second. 0 meters per second. It has to come to a stop or it can never come back down. So if the ball's moving and it never comes to a stop, it's going to move up and out into the outer space and go forever and ever and ever. So it has to stop before it changes directions. That's always the case. Even if I were to throw a ball against a wall, when it hits the wall, it's got to come to a stop for just an instant and then come back the other way. So it comes to a stop for just a billionth of a millionth of a trillionth of a second. It comes to a stop just for a tiny little instant. It has to come to a stop or it can never come back down. So good job on that. If you got that one right, pat yourself on the back. Great job. Now number 2. As a ball comes to a stop at the very top, what is the acceleration value? You're probably going to wrestle between two numbers. So throw me what that is now. What do you think the acceleration is? And the two numbers you're wrestling between, one of those is probably right. You got about a dozen of you in so far. Good, got about 20 of you so far. Very good, got well over 20 of you in so far, so that's great. And you're almost 50-50 on those two numbers. First block that I had earlier today, same thing. It was 50-50, 0 or 9.8. So if you're trying to wrestle between 0 and 9.8, good job, you're on the right track. Normally in school, it's one of those stupid things I do. At this point in the year, I hop on one of my big lab tables and I just wave my hands and say, everybody pay attention to this as I speak these answers. And it gets everybody's attention. And the reason I do that is this is one of those common things that are misconstrued in physics. People think because it comes to a stop, the acceleration has to be 0 as well. But that's not the case. So the 50% of you that guessed 9.8 meters per second squared, you are correct. You can pat yourself on the back. So here's what I do. I get up and stop top of the table. I tell everybody this. And then I say, this is going to be on the next test. And I also say, this is going to be question number 2 on the semester final. Now, will it be this year? Probably, if we have a semester final. But it's going to be question number 2 on the semester final. It'll say something very similar to a ball thrown straight up at the very top of its path. What is the velocity and what is the acceleration? And I always make a little deal with the kids, like, if you all get this right on the semester exam in a couple months, I will buy you cookies or ice cream or treats or whatever. And it's never happened. It's just one of those common things that people don't understand. So I want to make sure you guys understand this. It is 9.8, and I'll explain why for 2 reasons. And here's kind of a funny little side note. So then months later, we take the semester final, and kids will tell me later, like, Mr. Simon, it's funny because I read number 2, and I remember you were standing on the table that day. I remember when you teaching about this, but I don't remember what the answer was. So they remember me standing on the table to get their attention, but they don't remember the answer. Microphone's ready. See what I'm saying? Beautiful. Love you guys. All right. Why 9.8? Okay, 2 reasons. Let's look at it kind of mathematically first. Remember that you can never measure acceleration with just one velocity. Acceleration by definition is a change in velocity over time. which means I have to have a v1 and a v2. I can never in this universe ever measure acceleration if I only have one velocity. So quite literally, if a ball was thrown up and comes down, at the very top where the velocity is 0, I can't measure acceleration at that instant. But if I grab the velocity, like right there, and the velocity right there, and call that a v1 and a v2, and put the v1 and v2 in for delta d, v, and took the time for there and put that in a delta t, every time it comes out to be 9.8. Every time, regardless of what those velocities are. But here's even a better way of thinking about it. What causes this number of 9.8? You're going to answer me when I count down from 3, 2, 1, so get your microphones on. The answer ends in the letter Y. What causes the 9.8? 3, 2, 1. Let me hear you. Gravity. Gravity does. And here's the good news about gravity, or bad news about gravity. Gravity never takes a break. It's always working. So it's not like the ball goes up and at the very top, gravity goes, I'm gravity, I'm just going to take a break for a second. No, it doesn't. It's always pulling down towards the center of the earth. So even at the instant where the ball becomes 0 for velocity, gravity's still pulling, and our planet pulls at 9.8 meters per second squared. So it's always that number. Microphone's ready. Get it? Good. All right, you guys are wonderful human beings. So now let's go to page 37, number 3. So we did 1 and 2 on free fall. We did 1 last week. We did 2 on Monday. Now we're going to do 3. So an athlete wants to test its vertical jump. For those of you who don't know what that is, we do this with our football team, sometimes our basketball team. You know, we lift weights and stuff in the off season. And then we test vertical jump, which we have our athletes just jump as high as they can. And we have a measuring device that measures how high they can get off the floor. Somebody like LeBron James has a pretty good vertical jump. He could get a couple feet off the floor. Michael Jordan back in the day could get even higher. By the way, Michael Jordan is the best basketball player ever. So, athlete wants to test his vertical jump. He jumps and he's in the air for 0.76 seconds. We want to find his height and what his velocity was when he took off. For this, we can either do the up or the down. We don't have to do both, because what's going up is a mirror image of what's coming down. Personally, I like to do the down, because if I do the down, and I list out my 5 variables, I'm saying that even though this thing is going up and coming down, we're just going to do the down part. And if I do the down part, it's just like free fall, because I know the velocity at the very top is 0. So if I just do the down part, I'm starting here, which means my starting velocity is 0. My v2 will be the impact velocity down here. I know that if I'm going down, gravity will accelerate it at 9.8 meters per second squared, just like free fall. I'm told I'm going to be in the air for 0.76 seconds. Now here's the tricky thing. I'm in the air for 0.76 seconds. Only half of that is on the way down. So I've got to divide that by 2 to get the time for just the down part. So I got 0.38 seconds up, 0.38 seconds down. And just like that, I've got my 3 variables I can find for the distance and the velocity. Now I'm going to be solving for the impact velocity, but the impact velocity for symmetrical problems is the exact same as the initial velocity that I jumped with. I can solve for v2 or x first. It makes no difference which one I solve for first. I'm going to solve for V2 first because that means I can use equation 1, and equation 1 is easy peasy, extra cheesy. You can't go wrong with equation number 1. And it's all set up for me. So my V2 is 0 plus 9.8 times 0.38. I'll do this one for you. So I simply got 9.8 times 0.38. Looks to be about 3.724. We'll just go 3.72. So that's V2, but by definition, that's also the initial velocity for a symmetrical problem. As I mentioned last time, but just good reminder, anytime you know 4 things and you have a 5th thing to solve for, you can use any equation that has that 5th thing in it. So delta x is in 3 different equations, equation 2, 3, and 4. Makes no difference which one you grab, you're going to get the same number as long as you do the math for it. So let's use equation 2, because that's all set up for delta x. And I'm going to have you calculate this answer and send me a chat for the answer. Let's see if we all get the same number. So plug that baby out in your calculator and send me a chat. So far, so good. Remember the 1/2 in front. You've got about a dozen answers in so far. Good. Good, 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 good. All right, almost everybody got 0.71 meters. If you didn't get that, just double check. Again, you want 0.5 times 3.72 times 0.38. How much is 0.71 meters? Well, here's a meter stick. 0.71 meters is about 28 inches. So just over 2 feet. That's a pretty good vertical jump. That's a simple, straightforward, symmetrical problem. Now, you don't have to write this down, but just watch. Just watch. If I were to choose, well, first of all, am I going too fast, too slow, or just about right? So answer, here's what you're going to say. Too fast, too slow, or just about right? 3, 2, 1.
Just about right.
All right. All right, way to mumble. Nice job. All right. Don't write this down, but just watch. What if I were to choose the up part? So we chose the down part. What if I wanted to do the up? Well, then my problem would start here, and it would end there. So my 5 variables, now V2 would be 0 at the top. The acceleration would be negative 9.8 meters per second squared, but the time would still be half the time. So I'm using the same 3 numbers. That doesn't change. That's the same, just negative, and now V2 is 0. You would still use equation 1 to find V1. Now that would be 0, that would be your unknown, and that would be negative. When you subtract that from both sides, it becomes positive, and you're going to get the exact same answer. Then you're going to go to equation 2, That's still that. Now this would be 3.72, and that would be 0, but that's still going to be 0.38. You're going to get the same answer. So it makes no difference if you do the up or the down. You just have to be careful about which is 0, V1 or V2, and is it positive 9.8 or negative 9.8. And drawing a picture, literally, a little simple picture like this, literally does help. Microphone's ready. Get it? Good. So I only have one example there, so we're going to go to page 42, the homework page, and just do a couple examples from there. So your homework, let's check on the homework quiz. There was number 1, 2, 4, 5, 7, and 8. 7, by the way, there's a little typo there. Should say a soccer ball. You can't really kick a baseball, so soccer balls kick straight up. So no big deal if you didn't make that change, but we're going to make that change for next year. So I'm going to do number 9 and 10 for you, and maybe 6. I don't think we'll have time to do 6. We might do that later, but 9 and 10. So let's do number 10 first. So a gun fires a bullet at 320 meters per second straight up in the air. What's the initial velocity, or what velocity does it hit the ground, which is the same as initial velocity. So that answer is 320 meters per second. Because it's a symmetrical problem. It's going up, it's coming down. It's not landing on a roof. It's not landing in a tree. It's not off a bridge landing down into water below. It's just leaving the ground and coming back to the ground. So the initial and final velocity have to be the same. We want to find how high it goes and how long it's in the air. So my bullet's going up and coming down. I want to just do the down part. Just that part right there. So if I do the down part, I know it's going to start at 0. I know it's going to accelerate at 9.8 meters per second squared. And I know it's going to impact the ground at 320 meters per second. Because the initial and final velocity have to be the same. This velocity right there has to be the exact same as that velocity right there. If I did the up part, I would say V1 is 320 and V2 is 0. The acceleration should be negative 9.8 as it slows down the way up. I'm going to give you about a 3-minute head start on this one. So I'm going to play some music in the background for about 3 minutes. let's see how you did. Notice I changed my box to a cloud. So I use equation 1, solve for time, so I simply have 320 divided by 9.8, and I get 32.65. In your chat, see if you can answer this question. Why did I cloud that in? What would I have to do to get the answer that the question was asking for? Throw it in the chat if you know where I'm going here. Why is this not technically the answer? We got 2 people already in with the right answer. Nice, nice, nice. All right, so we had a couple different answers coming in. We had a couple explanations that came in. Excellent job. So we have some people saying we have to multiply that by 2. Some people say we have to divide that by 2. Some people are saying, well, that's just the time down. All that's good stuff. Something has to happen that has to do with 2. Is it multiply or divide? Well, this is just the time for the way down. So here's where a picture would actually help. As silly and as stupid as a picture might be, do I have to multiply by 2 or divide by 2? Well, if that's just the time on the way down, and I want the total time in the air, I have to multiply that by 2. So the total time it was in the air would be 65.3 seconds. 32.65 up and 32.65 down. All right, now we can go to solve for the distance. So I got 0.5 times 320 times 32.65. And I get a distance of 5,224 meters. That's a couple miles up in the air. All right, give me a thumbs up if you're with me so far. I want to make sure we're not going too fast here. All right, good, good, good. Seeing a lot of thumbs up.
Mr.
Excellent.
Simon?
Yes.
So in the equation to find the distance, like how far, but when you use like the initial time, so you don't use the entire time, only the half.
Correct, correct. And here, was that Madison? Great question, Madison. So here again, my picture will help me. So 32.65 down, so that using that down time allowed me to find that down distance. If I asked what's the total distance up and down, then I would either multiply that by 2 or use the full time up and down. We really never do that. We often just ask for how high did it go or how much distance did it fall. So just the down time will give me just the down distance, not the total distance it covered in the air. Great question, Madison. All right, that was number 10. Let's do number 9. Number 10, by the way, is very similar to number 8. In fact, take a quick peek at number 8, which you may or may not have done already. Number 8, you're going to get a value of like just over 10,000 meters. And a lot of times students have a problem like, Mr. Simon, I didn't see the 10,900 meters or whatever. I actually just rounded it up. So the answer to that is right there, 1.1 times 10 to the 4th. That's 11,000 meters. And the value you get for number 8 is almost 10,000 meters. So I just rounded it up to 11,000 meters. All right, number 9. The only thing different about number 9 is we're throwing the ball. So number 9 is a stone is thrown straight down from a cliff at 6 meters per second, reaches the bottom in 3 seconds. How high is the cliff? So the thing I want to point out here I mentioned it the other day in class, but I want you to see it, is if I throw the ball, so I'm not dropping it. The problem says drop, release, let go, V1 is 0. If I throw it down, now I just gave it an initial velocity, however, gravity is still the same. Once I let go of that ball, whether I drop it or throw it, once I let go of that ball, it's still only gravity that pulls it, and gravity on Earth pulls things at 9.8 meters per second squared. We're told it goes down for 3 seconds, so this is just a down part. All right, we threw it here at 6 meters per second on top, and you'll notice I draw a lot of pictures. The more pictures you draw in physics, the fewer mistakes you tend to make. So remember that for your homework, your quizzes, your tests, all that stuff. It's not mandatory, it just helps. So right there's 6 meters per second. V2 would be down here, but I wasn't asked to find that. I was just asked to find the distance down. So this would be using equation number 4. Because we're not worried about V2. So I got V1, A, X, and T. Often when we use equation 4, V1 is 0, but it's not this time. Right, it's 6 meters per second. Don't forget to square that 3 on the end. That's a common mistake with equation number 4 is forgetting to square. So let's have you ram-a-lam-a-ding-dong that on your calculator and shoot me a chat when you get the answer. Ooh, Annie and Molly were pretty quick on that. Nice job. Keep coming. Got a handful of answers in. Give me a few more here. Now they're rolling in. Nice. Most of you got what I got. So 6 times 3 plus 0.5 times 9.8 times 3 squared is 62.1. That's almost 200 feet. All right, send me, well, I'll give you 30 seconds here to finish up. If you have any questions, please just pop your microphone on and ask away, because Madison asked an awesome question last time. I'm so glad she asked that. And normally if this is in class, I'd be walking around the room as you're doing these, and it's a lot more easy for students and teachers to know how you're doing. So please, by all means, ask a question if you have it. Then, do me a favor, chat me a 3 if you're like, yep, I understood this stuff today. 2 if you're like, yeah, you know, I think I got it, it's coming to me. And a 1 if like, I have no idea what we were doing. Oh, I love the 2.9 there, Logan, that was pretty cool. 2.99, nice, nice. All right, I got a lot of 3s and a lot of 2s, so that means we're doing pretty well. And again, if you need a little extra time, just come to ASR. Even got a 4 chatted to me, outstanding, nice. So just a reminder now, you have the homework quiz, which is due Sunday night. So 1, 2, 4, 5, 7, and 8. And the homework quizzes, again, are the exact same verbiage, the exact same lingo, and then we throw 1 or 2 extra ones on there. So do the homework first, and then it makes the homework quiz very easy. That's what we're supposed to be doing. So, all right. Remember, who loves you and has 2 thumbs? Who loves you and has 2 thumbs? Come on, let me hear you.
Mr. Simon.
Come on, everybody. What do you got? You betcha. Mr. Simon. Loves you, has 2 thumbs, man. Hey, great job. We will just touch up a few things on Monday, and then we're going to start with something called vectors on Monday. And again, if you want to know how to do the asymmetrical ones, just for your own knowledge, we'll have that video loaded on Buzz before the end of the day. So if you have any questions, feel free to stay on when everybody logs off. Otherwise, I love you guys. Have a great weekend, and we will see you next week, Monday. You're welcome. You're very welcome.